Thank you, ma'am, for such a warm introduction. Thank you so much. Are the presentation rights with me? Okay. Yeah. Just a second. Huh? Please confirm if my screen is visible. Thank you. A very good afternoon to every one of you. Myself, Dr. Neelam Singha. I'm currently working as an assistant professor in the Department of Mathematics, School of Technology, Pandit Deendayal Energy University, formerly known as Pandit Deendayal Petroleum University, Gandhinagar, Gujarat. Today, we all are here for a discussion on some part of my research. So throughout the presentation, for network issues only, I'll be keeping my camera off. Okay, I hope that's fine with you because I have observed that there are a lot of network issues here. Okay, so please allow me to do that. So today I'm here to discuss some part of my research work, and I have chosen a very interesting problem, that is applications in real world problems. To be very specific, I'll be focusing on some cancer models which can be solved with the assistance of fractional calculus tools. So the title of my presentation today is Fractional Optimal Control Problems in Biomathematical Modeling. How can we use the mathematical models to solve the cancer problems or similar real world problems? So as I already stated, that I'll be dealing with, or I'll be discussing the applications of fractional calculus. So it is very important for us to understand what actually fractional calculus is. I hope every one of you know a little bit about fractional calculus or maybe more, and having different interpretations of what a fractional calculus is. I am going to share a version of what I understand and what I have used fractional calculus. So basically, we all are aware about nth derivative of a function. Say why? Correct. All of us are aware about the nth time derivative. And we are always focusing on n to be an integer. I'm saying integer because if we take a negative ones, I'm not saying positive integers only, because if we take a negative ones, then we can talk about integrals, correct? So what if n is not an integer? There's no limitation now. So what happens if it is not an integer? The same question was asked by L'Hopital. Yes, L'Hopital in 1695 asked Leibniz the same problem, or the same discussion was going on when the notion of nth times of derivative of a function arrived. That was a long way back, correct? And to which Leibniz responded that it is an apparent paradox from which one day useful consequences will be drawn. And today, if you look at various research problems, as many as you can, you will be finding the applications of fractional calculus. And why paradox? Because at that time, if we look back, there were no applications or interpretations, we may say physical or geometrical interpretations of fractional derivatives or integrals present at that time. So basically, we were discussing, or we wish to discuss about some alpha times derivative of a function. Means what happens if we remove the restriction on n to be an integer. Here we land on the concept of fractional derivative or fractional integral. This is the extension of integer order derivative where the restriction on n to be an integer is removed, and we can explore the various applications. One more thing I would like to discuss is this. I find actually very interesting. We are differentiating a function, say f, once, twice, thrice, and so on. This is usually we do in any of our problems. Or we are integrating it once, twice, or so on. Correct? But what's in between? We all study mathematics, we all do research. We cannot simply neglect, or we cannot say that nothing happens in between this range if we do not have any proofs. Correct? But later, after Leibniz and Lapidus's discussion, we came upon the notion of alpha times derivative of function, where alpha lying between 0 and 1 means we are talking about lower order derivatives. We know about one time derivative, double derivative, and so on. So the derivatives existing in between are nothing but the lower order derivatives lying between integer order derivatives, or what we can say. I hope every one of you, and not I hope, actually, I know that every one of you are very much aware about interpolation, correct? What we do in interpolation? We have some data known at certain points, okay, and we arrive at an approximation which gives us the knowledge of function in between, correct? So if we look at fractional derivatives or fractional integral, we can say the same. Okay, we have here integer order derivatives. Say I'm writing y1, y2, we can say first derivative, second derivative, and so on. So if I am writing y alpha, so these integer order derivatives are nothing. If you can look in the way of interpolation, then each interpolates the fractional order derivatives. Okay, so in easier way, I can say that this is the lower order or lower derivative of y. Correct? This is what I have presented here as well. Because sometimes we simply understand it as a generalization, but it is more than that. Actually, if we again go back, then it originated a long back, but it was not very popular among researchers. The problem being, we know the physical and geometrical interpretation of classical derivatives or classical integrals. If I ask any one of you or anyone, you will be telling that we can relate it to velocity, we can relate to acceleration, correct? We can talk about approximation, linear approximation with classical derivatives. Yes, we can talk about rate of change, but what physical or geometrical interpretations or applications we have for fractional derivatives? First, I will talk about geometrical or physical interpretation, then I'll come back to applications. Okay, so let me draw for you. If I'm talking about classical derivative, To be very specific, first order derivative. Okay, then I hope every one of us understands this. Tangent at this point. Yes. But here though we are talking y alpha, not y1. Means as soon as I'll be changing alpha, I'll be getting one curve, isn't it? Because alpha is lying between 0 and 1. I'll be getting various curves, various lines. So these are nothing but frictional tangents. And what happens actually if you decrease the value of alpha, then the area, this area which this tangent is bounding, gets increased on its own. The value of alpha increases, the area decreases. And this seems to be very interesting. One more property which the fractional derivative preserves is the approximation. We know that the classical derivatives can be used for approximating a function at any point linearly, isn't it? But how fractional derivatives can help us? It actually gives us a, it also gives us approximation, but not a linear one. We can approximate a function non-linearly. That is the main advantage of fractional calculus or fractional derivatives. Moreover, we whenever we talk about differentiability now, function, suppose I'm talking about this function, everyone, no, correct, f of x is equal to mod x. We know that this function is not differentiable, isn't it? Why? Because of the problem of continuity. But this is not the case with fractional calculus. This is not the case with fractional derivative. Whether a function is continuous or not, you can talk about its derivative. You can talk about its integration. So that is the main advantage if we talk about the fractional derivatives or fractional integrals. Let me quickly go back so that I can finish the real world application as well. So throughout my research, I have specifically worked on 3 different kinds of problems. 2 are related to each other, but one is not. One is very different. So I have dealt with fractional calculus of variations, fractional optimal control problems, and the last but not the least one is fractional order convexity. Means defining the convexity with the help of fractional order operators. When I say operators, I quickly mean derivatives or integrals. So I'll be focusing here today. These both are related. This FOCP or optimal control problem is nothing but the extension of calculus of variation only. So I'll be discussing more about FOCP today, it means fractional optimal control problems today. So let me take a very basic problem first, so that every one of us can at least understand that how we can apply FOCP and what I have done in this problem. Okay, this is a very basic optimal control problem. I always like to give this example so that the basic difference between calculus of variation and optimal control problems can be understood. Suppose we want to pass or we want to move from point A to point B and I want to find the least path. Correct. You can tell me that, of course, the straight line will be the least path. Correct. Okay. Now I am adding certain constraints to it. Okay, these are say the constraints 1, 2, 3, and 4. 4 constraints I have added. You can add as many as you can, or you can remove some. My question is that, or what I want to discuss is, I want to move from A to B and touching these in any order. Okay, order is not necessary. In any order I wish to, but I need to pass through all these points. Fine. Then there will be certain way you can describe, or many ways, correct? I can move like this. So there are very, there are many controls. I'm calling them controls. Correct. But my problem is not finding these controls. My problem is finding the optimal one. There are many paths I can choose, but I have to choose the optimal one. Optimal in the sense of maximizing the profit or minimizing the risk. Okay, so I need to find the problem. I want to find the similarly, if you talk about or if you consider a real world model, okay, let me just quickly show you a model uh, to which you can relate to this topic. Okay, yes, this model. Okay, so I'm referring to equation number one. This is a simple integration if you see, isn't it? Or if I remove this f term, or you do not know what are t, a, u, and anything else, then you will simply see this one as a control problem. Okay, what we want to do here, we want to find the control optimal one u such that this functional is minimized. Okay. Very basic thing. Every one of us can understand. Okay. And we have added some constraint. Don't look at the left hand side, just right hand side. Some equations are provided to us. Fine. So we want to minimize the functional given certain constraints. Okay. So this is a problem of optimal control. Only what I have done, instead of taking classical derivatives, we are dealing with fractional derivatives. Here, this term, okay, d alpha denotes the Kapotow's fractional derivative. Fine. And let me be very specific about this problem. This actually a very famous problem on minimizing the dose of drugs or the dose of chemotherapy which is given to patients having cancer, okay, certain form of cancer. Now, what we need to do in this case, we need to minimize the dose of drugs given to patients, correct? In a very simpler way. This model may look complicated, but actually, if we try to understand, this is just given a optimal control problem, and with these constraints, I want to minimize the function. Right? Here, there are notations involved. In this model, T denotes the concentration of tumor cells, N is the concentration of immune cells, and C is the population of circulating lymphocytes, and M is the amount of drugs, U is the amount of anti-cancer treatment. Note that here I have mentioned drugs as well as anti-cancer treatment separately because whenever a patient is going through some treatment, some chemotherapy or other anti-cancer treatment is given to us together with some drugs as well, some medicines as well. So M denotes the medicines and U denotes the uh, treatment which is being given to the patient. Okay, so my aim is to minimize this functional together with controlling this U. U is amount of the treatment, anti-cancer treatment, which is given to patient. Okay. So now this is simply a mathematical model to us. If we simply look at in our perspective, this is a simple problem which we can easily solve, and we have already solved many models. Okay, whether it relates to some real problem or not, but we have solved many models with several numerical techniques. Why numerical techniques? Because we know that all the time analytical solution may not be available with us. We may find it difficult to find the analytical solution. So we move towards the numerical solution or the approximate solution, the solution which is very much close to the exact one. Correct. So here, what I have done, I have used a Domian decomposition method. I I'm very much sure that uh, people working with numerical analysis well aware about the decomposition method. So I have used I have implemented the Adornian decomposition method to solve this problem. And every one of us know that in Adornian decomposition method, whenever we apply to it, we get the necessary optimality condition with the help of this. Correct. So let me go back quickly so that we can understand the necessary optimality conditions, and then we can talk about the dominant decomposition method. Okay, here I have obtained the necessary optimality condition for the given problem. Means to optimize this functional, I need to deal with these set of differential equation, fractional integral differential equations. Okay, so I have chose a dominant decomposition method. What we do in a dominant decomposition method, we approximate the state variables. Okay, these are these, except u is the controlling variable, t, n, c, and m. These are the state variables. So we approximate the state variables with series solution. Correct. With a infinite series. Okay. So here, with the help of Adornian decomposition methods, we have approximated the state variables as infinite series. Okay, and then after certain steps, means after reaching certain point of accuracy which we want, we will terminate it, and we will be arriving at some nth order approximation. Okay, so by applying Adornian decomposition method, what we get the recurrence relation of state and control variables. Okay, with the help of recurrence relation, what we are able to obtain, we are able to obtain the nth order, you can say kth order approximation of the solution which is needed to us. Only these terms are looking complicated, but trust me, these are not. Once you apply ADL, becomes very easy. Okay, these all numerical part I have done with Mathematica. If you wish, you can solve with MATLAB as well. Okay, I would like to discuss about the graphical parts. Yes. So here, after solving that problem with the help of the domain decomposition method, whatever approximation we got, we plotted it. Okay, and these are some of the plots which I want to discuss. The first one is the plot of tumor cells, and the second one is the plot of immune cells for various values of alpha, and time is also moving here. T is plotted here. So you can see that the tumor cells are increasing and immune cells are also increasing nature here. Okay, as we vary alpha. You may ask that tumor cells are increasing, uh, but our problem, if you see, was to optimize the amount of drugs given to the patient. Correct. So here are again it's a plot of lymphocytes and amount of medicines given, but our control variable is U, this one, and its nature can be easily observed here. Whatever value of alpha you take, the plot of U is decreasing. Correct? Means the amount of anti-cancer treatment which is being given to the patient, okay, decreases with time. Because why it is needed? Because whether you talk about chemotherapy or any other anti-cancer treatment, it comes with lots of side effects as well. So it is very important that with time the amount of these drugs should be decreased. Okay, must be decreasing in nature. So this is the nature of the control variable which I have plotted here. Okay. Now, one may also ask, or you may get confused that what is the sense of various values of alpha, and is this a single problem? Then the answer would be no. This is not one single problem. Okay, this one. As soon as you change the value of alpha, okay, the problem is a specific problem related to that alpha. Okay, so this is a class of problems which I have presented here, a class of problems for fractional optimal control, and the solution mentioned here altogether is also a class of solutions. Okay, so I am not required. What is the benefit? I am not required to solve each and every problem separately. Just by solving the model and varying the value of alpha, I can give the solution very easily. So these are the solutions I have obtained. Okay, one more thing I wanted to discuss. Yes, that while applying a domain, what are the advantages and what are the disadvantages? What happens that when we apply a domain now, then first I'll be talking about the computation. The computation becomes very lengthy because every time we are required to talk or we are required to compute the domain polynomials, these are very easy to compute if we are dealing with classical derivatives, okay, or classical differential equation, integral differential equation with the integer order, correct? But as soon as we come with fractional derivatives, these computations are really difficult to compute. So here, the computational difficulty is that you may also observe in these computations, okay, some of the computation, if you allow me to show here. Yes, after third or fourth iteration, we come with a very difficult functions, and these are difficult to obtain if you are doing it manually. Up to third or fourth or fifth iteration we can do, but of course we have smart computers with us today, so it's very easy if we are doing it with some software. But yes, manually these are difficult to obtain. But what is the advantage? Advantage are that if you are applying a domain now, then these set of differential equations are simply broken down into simple linear equations, correct? Or very simple equations which we are able to understand very easily. Like if we have simply approximated it with series solution or with infinite series, then what happens? We are simply finding, once we have obtained one approximate solution with the help of recurrence relation, we can obtain the next ones easily. And after certain steps, we can simply stop it. Like I have done here. First, I have found initial approximation like x1, x2, x3, and so on. And after that, we have truncated it at fourth step. Yes. And we simply sum them up, truncated at fourth step, after fourth step, and we get the approximation. Here xi is x1 was t, x2 was n, and so on. So we can easily find the control variable. We can even find the state variable. And most important thing is we can observe these function as a function of time t. It's not that we are only dealing with some numerical values. You will get a function of time t for every state and control variable. Like if this is the concentration of immune cells, n is the concentration of immune cells, then you can see that at what time, or suppose after 10 years, what will be the approximate concentration of immune cells. Same goes with tumor cells and so on. So this is the main advantage, that we are plotting them as a function of time t, not discrete values. And with this, I would like to end this discussion on fractional optimal control problems and how we can use it to real world problems. These are some of the conference and workshop I have attended, so let it be here. Okay, thank you for giving me this opportunity, and trust me, if you take any problem on biomathematical modeling, you can easily uh, approach it with the help of fractional calculus. You can understand that what happens, that without, if we replace the classical derivative with fractional derivatives, and this is what I understand with fractional derivative, that what happens if we apply the same approach or if we apply the same method but we replace the classical ones with fractional order derivatives. And this was the same thing that was said by uh, Leibniz, that one day useful consequences will be drawn. And today, if we see almost every real world problem, at least if you're not able to solve, we are trying to see what happens if we apply fractional order derivatives. So with this, thank you everyone for having patience and listening to me. I would like to hand this over to the coordinator. If there are any questions or any discussions to be made, let me know, please.
Hello, ma'am.
Hello.
Thank you so much for the talk. It was really interesting and it was very nice presentation.
Thank you.
Can you tell me what is the difference between state and control variable you were picking up there?
Yes, why not? Okay, let me start the PPT. Just yeah. Okay. Here we are. Let me go back to a very easier one. Okay. I hope you can see this page, correct?
Yeah.
Yes?
Yes, yes. I can see.
Okay. So let's look at this integration. Okay, this is a functional of u. Okay, this is a function of x is a function of t, ut and t. Okay, so as soon as we will change the value of x, okay, this will entirely gets changed. Okay, this j will be a function of u. This whole integration is a function of u. So u is the control variable and x is the state variable. At different states, you want to check what will be the control. This is the optimal trajectory. Here, xt, if you simply see at this function, okay, xt is the state variable, different states. You can simply relate it to different state, which will optimize the optimal control, or which will optimize the control, which we want to find. I hope I'm
Yeah.
audible.
Oh, yeah, you are audible.
Is there anything else from the audience?
I think Annapurna Panda ma'am has raised hand. So please, ma'am, go ahead. Ask your query. Panda ma'am, anyone else having any query? If not, let me officially thank. At the end of 49th Siksha Anusandhan weekly academic lecture, I shall take the liberty of proposing the vote of thanks. We thank the speaker, Dr. Neelam Singha, for giving such an informative talk on the topic fractional optimal control problems in biomathematical modeling. Our thanks are due to colleagues, research scholars, and students in the audience. We express a big thank to Dr. Manoj Ranjan Nayak, the Honorable President of Siksha Anusandhan Toby University, who has always been a source of inspiration to all of us. I extend our thanks to Dr. Manoranjan Pari, the Chief Coordinator of Center for Data Science, for the necessary supports. Lastly, I, on behalf of Center for Data for data science, Siksha Anusandhan Team to be University extend our heartfelt thanks to all. Thank you all. So here the talk ends. I think we should stop this. Thank you, ma'am,
Thank
and
you for
thanks
having
everyone.
me, for giving me this opportunity in such a short time. But I think it
Yeah,
was good meeting you all.
yeah, you agreed in
Thank you.
such a short span of time.
It's not a problem. I'm always happy to be a part of any program in ITR because I have already worked there. So there's a connect.